Hello dear students, welcome to the 7th video in the series Organic Chemistry, Some Basic Concepts. The topic we are taking up for today is intermediates formed during the course of an organic chemical reaction. What is an intermediate? When a substrate is attacked by a reagent, new bonds are formed, old bonds are broken, and it results in the formation of an unstable form, what is called as an intermediate. This intermediate, being unstable, gives rise to what we call as the products. Now, the products of a chemical reaction are dependent on the reaction conditions, the reagent you have chosen, the intermediate which is formed during the course of a reaction. We are studying three primary intermediates. I'm not talking about carbenes and nitrines right now because the primary ones, carbocations, carbanions and free radicals are the ones which we study at the basic level and which play a major role in our basic study of organic chemistry. Carbocation, a carbon with a cut, is what we call as a carbocation. In other words, this will be an intermediate where the carbon atom will carry a positive charge. For example, if I talk about ethanol breaking down, C2H5OH, when it breaks down, it gives me C2H5 positive. This is what we call as a carbocation. That means a carbon carrying a positive charge. So as you can clearly see over here, it is resulting in the formation of ions. What type of cleavage or fission results in the formation of ions? It is heterolytic fission. So carbocations are formed by heterolytic fission of a substrate. Since the carbon carries a positive charge, let us understand what will be its structure. Carbon here, ground state configuration 1s2, 2s2, 2p2. Excited state configuration 1s2, 2s1, 2p3. 2s1, 2p3. Now here it is positively charged. The carbon here is positively charged. So positively charged means it loses one of its electron. So it loses this electron. It is left with 3 electrons here in its valence shell, which will have a tendency to pair up. They undergo sp2 hybridization. That means we have one p orbital which has not taken part in hybridization, which is indicated by the dumbbell shaped orbital over here. The remaining 3, sp2, that means 1 of s and 2 of p. 1s and 2p together combine to give us 3 sp2 hybrid orbitals. These 3 will align themselves so that they are maximum distance apart, which gives us a trigonal planar shape. So it is these 3 are in one plane, whereas our p orbital here is perpendicular to this plane. 3 electrons it had, 3 electrons it has taken up while sharing. In other words, this carbon has 6 electrons in its valence shell. What are the various types of carbocations and what is their stability order? For any of the ions that we'll talk about, carbocation, carbanion, free radical, we shall be using the terms tertiary, secondary, primary and methyl. What is tertiary? Tertiary is when the carbon carrying the charge or the functional group is attached to 3 other carbon atoms. Secondary, the carbon carrying a positive charge is attached to 2 other carbon atoms or alkyl groups. Whereas the third one would be a hydrogen. A primary carbon, carbon carries a positive charge attached to only 1 other carbon atom. Methyl is CH3. Now, Let us see the stability order. Here we shall recall our knowledge about resonance and inductive effect and hyperconjugation. Now see over here, the alkyl group is electron releasing. What you have to understand over here is this carbon is positively charged. But there is an alkyl group with which it can also undergo hyperconjugation. If you go back to the video on hyperconjugation, we had spoken about hyperconjugation taking place over here when the alpha carbon has hydrogen atoms attached to it. So in other words, there is a possibility of 1, 2 and 3 hyperconjugative structures. 3 over here, 3 over here, assuming this R is methyl group. So in other words, there are 9 hyperconjugative structures possible. Here, again assuming CH3 and CH3, there will be only 6. Here there will be only 3. What we had said was more the number of hyperconjugative forms that an ion has, greater will be the stability. In other words, this carbon is quite safe. It can borrow electrons from so many options, whereas this one can't. This one can borrow only from one set. This can borrow from two sets I'm talking about, 2 alkyl groups. So with the result, what will happen is, more is the capability of this carbon to share electrons with another atom or group, greater will be the stability. Just think of your situation. If you need any help, more is the number of friends you have, more stable and more stress-free you are. Whereas if you become a loner with no help and no support, then it becomes difficult to survive. So here what we have over here is, there is the possibility of hyperconjugation. Hence, tertiary is more stable than secondary. Secondary is more stable than primary, and primary is more stable than methyl. Another factor which comes into play is if there is a benzene ring attached. That means this carbon which has a positive charge is actually a part of the benzene ring. Then resonance also comes into play, and we have to account for that as well. These are positively charged, carbocation, and a carbon with a positive charge. This is positively charged. With what type of species will it prefer to interact? With another positive one, there will be repulsion. So it tries to attach itself to something which is negatively charged or has an excess of electrons. In that case, they are electron acceptors. They accept electrons, hence they are also called as Lewis acid. A simple mnemonics is acceptor acid. So Lewis acids are electron acceptors. Since they are attaching themselves to something which is carrying a negative charge, that means they are reacting with nucleophiles. That means nucleus loving species. They themselves will become electrophiles. Coming to the second intermediate over here, carbon anion. An anion where the carbon carries the negative charge. As simple as that. So as we said earlier, cations and anions are formed by heterolytic cleavage. Here we have shown a carbon with a positive charge. There are many cases where you get carbon with a negative charge. Here carbon, again coming to the configuration, 1s2, 2s2, 2p2 is the ground state electronic configuration. We come to the excited state. Now if you notice, carbon has a negative charge. In other words, it has taken up electron from another atom. So this is paired up. Now we are left with 1, 2 and 3. So it pairs up with 3 other hydrogen atoms or carbon atoms depending upon what type of alkyl group we are talking about. These undergo hybridization and they are now sp3. So 1 of S and 3 of P gives us a total of 4 hybrid orbitals called as sp3 hybrid orbitals. Now these hybrid orbitals will try to arrange themselves so that they are maximum distance apart. Now that maximum distance apart happens only when we talk about a tetrahedral structure like this. So it should be 109 degrees 28 minutes. That should be the bond angle like in the case of the structure of methane. But a small thing that we have to keep in mind is we have one lone pair. That means a pair of electrons which has participated in hybridization but is not involved in bond formation. So this is our lone pair. So this lone pair repels the bond pair over here. So lone pair bond pair repulsion is little more than the repulsion between bond pair and bond pair. So this angle, which should according to tetrahedral condition should be 109 degrees 28 minutes, actually becomes 107 degrees. Very much similar to the structure of ammonia, and that is how we have the structure of a carbon anion. This is how it is, where the top is just being occupied by the lone pair of electrons, and that is how we call it as a pyramidal structure because it resembles a pyramid. If you see over here, 1, 2, 3, 4, 5, 6, 7 and 8. It has 8 electrons in the valence shell of the carbon carrying a negative charge. Coming to the stability order, as I said earlier, you'll talk about tertiary, secondary, primary. Here in each of these cases, the carbon is carrying a negative charge, right? Now what will happen is carbon is already loaded with electrons. Alkyl groups are electron releasing. So this alkyl group releases more electrons. That is, they are having a plus I effect. So something which is already loaded, it is like you are carrying a pack of books on your head and somebody puts more on your head. So what will happen? What will be the consequences? You will tend to collapse, right, under the weight. The same thing happens over here. The alkyl groups, they actually load the carbon so much that its stability actually decreases. Come to the secondary. Here there are only 2 alkyl groups which are electron releasing. Primary, there is only 1. So you can definitely easily carry the burden of 1 more person compared to when you are to carry the burden of 2 more people, and of course carrying the burden of 3 more people becomes very, very difficult. Hence we say the stability order is reversed. We say primary is more stable than secondary, which is more stable than tertiary. This is exactly reverse of what we had done in carbocations. They have a tendency to donate electrons. They are electron donors. Hence they are called as Lewis bases. And they will have a tendency to combine with something which is positively charged. That means something which needs electrons. So they themselves will combine with electrophiles. Coming to the third. If you feel that you're getting confused, I would suggest that you pause the video, take a break and come back to it. It will help you to imbibe as well as understand it with greater clarity. It's not necessary that you need to do all in one go. It gets very, very confusing, especially if the fundamentals are not clear. If you are having problem in understanding the terms like hybridization, sp3, sp2, I would suggest that you have a look at the other videos we've loaded onto the this channel, where we have thoroughly gone through sp2, sp3 and sp hybridization in complete detail. You will also find a write-up of this on the website, on the Google site, Learning Chemistry is Fun. That is for easy reference, and supposing you need to understand something in greater detail, you are most welcome to visit that site. It's a free site, no charges, it's completely voluntary. Coming to free radicals. They are radicals which are free. In other words, they are like atoms. How are they formed? If you remember earlier video, we've spoken about homolytic fission. That means the fission of the bond takes place in such a way that each atom goes away with its own electron. In other words, they will have an unpaired electron on them. But technically they are neutral, because this electron originally belonged to them only. It is just that after breaking up the ties, they have gone their separate ways. So this is formed by homolytic fission. Let us come to the structure. Carbon 1s2, 2s2, 2p2 ground state, excited 2s1, 2p3. Now if you notice over here, there is one electron which doesn't have a pair. So let us leave it like this. And 1, 2, 3. 3 electrons pair up with either hydrogen or with another carbon, depending upon what type of free radical intermediate we are talking about. This unpaired electron is untouched. So we are left with 1 of S and 2 of P. They undergo hybridization to give us an sp2 hybridized state of the carbon. The last p orbital again remains untouched. So we have 3 of these bonds in one plane like this. They are all in one plane, right? And we have a p orbital on aligned perpendicularly like this. sp2, 1 of S and 2 of P makes it a total of 3. This is sp2 hybrid orbit, this is sp2, this is sp2, and each one of them is undergoing sigma bond formation with the other atom. The p orbital is left with an unpaired electron. So we have 1, 2, 3, 4, 5 and 6 and an unpaired electron. So there are 7 electrons in the valence shell. This is where the difference comes in between the carbocation and the free radical. Again, coming to the stability. Okay, mind you, free radicals are actually represented by a dot at the top indicating the unpaired electron. So if you notice over here, in each of these structures, we have put a dot over here. This dot indicates the unpaired electron. So just like carbocations and carbon anions, we have tertiary, secondary, primary and methyl free radicals. Again, hyperconjugation comes into play. 1, 2, 3. 3 alkyl groups. In other words, if we are considering that they are all, let us suppose, CH3 groups, total 9 hyperconjugative structures, 6 hyperconjugative structures, 1 hyperconjugative structure, none. So here it has a lot of 3 friends, here it has only 2, here it has 1, here it has none. So with the result, which of these forms will be most stable? Yes, tertiary is more stable than secondary, which in turn is more stable than primary, and which in turn is stronger than a methyl when it comes to stability. One free radical will have a tendency to combine with another free radical in order to pair up its unpaired electron. These are tabulated points of intermediates in organic compounds, carbocation, carbon ions and free radicals. I want you to take it in the form of a chart so that you have a comparative account and a clear account in front of you. If you want a detailed information on this, I would request you again to visit the website Learning Chemistry is Fun. It's a Google site, Learning Chemistry is Fun. Do let me know your feedback. Thank you for watching.